the next thing we're going to focus on here is this idea that not all resonance contributors are created equally. And so let me just give a very simple example here. We talked about the carbonyl group, how it is a pi bond that's located between two atoms of differing electronegativity, and so it has this resonance structure available to it. Okay. Cool. So these are these two perfectly valid resonance structures, resonance contributors rather, for a carbonyl bond. Doesn't mean that they're both equally stable or that they both play the same role in its chemistry. And in fact, they're not. As you would imagine, this one over here is quite a bit less stable than the other one because the oxygen and the carbon have formal charges associated with it. Sort of like how a nectarine is a little bit more of a peach than it is like a plum, right? It's more like a hairless peach. So you wouldn't say it's exactly 50-50. Same thing sort of over here. But again, a nectarine is still just a nectarine, and that's the same thing over here. Even if this is a less stable resonance contributor, it still will impact the behavior of that particular molecule, or in this case, this particular bond. A carbonyl bond, in a carbonyl bond, that carbon has a relative deficit of electrons. It's a bit of an electropositive center. And that's in part due to the contribution of this resonance contributor. Okay, so just because you can draw resonance contributors, it doesn't mean that they're all equally stable. However, being able to draw any amount of resonance contributors has a stabilizing implication for your molecule. But now we're going to try to go in and spot which are more stable resonance contributors and which ones are going to be less stable. Okay, so formal charge will generally decrease stability, just like we saw before. This is especially the case if you're putting a formal charge of +1 on the more electronegative atom and -1 on the less electronegative atom. Okay? Right, so the more electronegative atom should have the negative charge. The other thing that will decrease the stability of a resonance contributor is any incomplete octets, right? Incomplete octets will decrease stability. Complete octets, though, that means good stability. Okay, so let's draw out different resonance contributors. This is acetic acid in its acid form, as well as what's called the conjugate base. And we'll remind everybody of that terminology next week. But the only difference between these two is right, the conjugate base has actually already donated its proton. So we're going to look at the resonance structures for here. Notice that this molecule does have resonance available to it. It's one of the patterns that we spotted, which is a lone pair located in the allylic position. So I can bring that down there, those electrons up there. Oh, line. All right, but everybody take a second and make sure that you can fill in charges here. Follow my arrows to fill in charges. This oxygen would have a -1 charge, 3 lone pairs. And this one would have a positive charge. So one of these resonance contributors is way more stable than the other one. Okay? Oxygen does not want to have that lone pair, never mind the fact that we've created formal charges on 2 different atoms. So this is a low contributor. Doesn't actually impact the chemistry of this molecule very much. On the other hand, when we look at the conjugate base, now we have this pair of electrons. Again, we have a lone pair located next or in a vinyl position. That's, again, the pattern that we're spotting here. And this lone pair can come down. Those pi electrons can come up. And now if we look at my other resonance contributor here, it's actually identical to the first one. One of the oxygens has a negative charge on it. The other one is neutral or has a formal charge of 0. And this is now a great resonance contributor. It's equally stable. And this is just showing how this negative charge is being dissociated throughout this pi bonding system. So this is an example where the resonance contributors, your two resonance contributors, are equally stable. And so we would expect this to have a very big role in the chemistry of it. We would expect these two bonds to be exactly identical in length, for example. Another way to assess stability of a resonance contributor is to take into consideration carbocation stability. So not all carbocations are created equally, and we'll explain why a little bit later, but for now, I just want you to know this is the deal. The least stable carbocation is going to be the methyl cation, or when there are only hydrogens attached to that positively charged carbon. Notice the naming here is similar to what we've seen before, primary, secondary, tertiary. You're talking about how many other carbon-carbon bonds there are, right? How many carbons are bound to that positively charged carbon. The tertiary carbocation, or when that carbon is bound to 3 other carbons, is going to be the most stable. And it's a sliding scale from there, right? So, when you're assessing stability, so for example, I can do, let's do one like this. This meets one of our patterns because I have an allylic positive charge. Well, this pair of electrons can come over here. This will be my first resonance contributor. And then the last step would be there. All right, so if I asked you which one of these is going to be the most stable resonance contributor, what one would you think? It's going to be the middle one here, because that's the one that has a secondary carbocation. And again, that's not to say that we just wouldn't draw these or anything like that. This is all about just looking at all your resonance structures and determining which one's going to be the most stable contributor. Oh, I'm sorry, all your different contributors, and determining which one's going to be the most stable. Right, so in this case, I can draw all the resonance structures available to this molecule and identify that this one here with this secondary carbocation, that's going to be the most stable. Okay, so make sure to practice that, being able to identify which groups demonstrate resonance and then which resonance contributors are the most stable. And then we can finish things off with resonance 3.